Welcome to the deep dive.
Great to be here.
Today we're jumping into something pretty fundamental. Powers, exponents, and roots. Think of it as getting the essentials from our source material.
Yeah, sort of extracting the core ideas without all the textbook exercises.
Exactly. Our mission is to, cut through the definitions, really get the mechanics, and see why these tools actually matter for you.
Sounds good. Where should we start?
Okay, let's unpack the basics first. What are powers and exponents, it seems like?
Well, just shorthand for multiplying the same number over and over.
That's exactly it. Pure efficiency. Instead of writing out, say, $5, 5 times 5 times 5, 5 times 5 times 5 times 5, $5, it's tedious, right?
Yeah.
You just write 577. The main number, 5, that's the base.
Mm-hmm.
And the little number up top, the 7, that's the power or exponent. It just tells you how many times to multiply the base by itself.
So it's basically a counter for the number factors.
Precisely. And once you have this shorthand, you start seeing patterns in how they combine, the rules. The rules. Okay, yeah, this is where it gets interesting. How do these things play together?
Well, the first big one is the product law. What happens when you multiply two powers with the same base? Like 344 times 3 under 600s.
Okay.
Think about it. 344 dollars is 4 threes multiplied together, and 3 and 666 is 6 threes multiplied. If you multiply those results together,
You just end up with a longer string of threes, 4 of them, then 6 more, so 10 threes total.
Exactly. So you just add the exponents. $4 plus 6 surge gives you 3 and 10. You're just combining those groups of factors.
Got it. Makes sense. So if multiplication means adding exponents, division must mean subtracting them.
You got it. That's the quotient law. If you have, say, $308 divided by $36, you've got 8 threes on top and 6 threes on the bottom.
So 6 of them cancel out.
Precisely. You're left with 2 threes on top. So you subtract the exponents, $3, $8, $6, 3, 2, 2, 2.
Okay, that holds together nicely. What about raising a power to another power? I saw 23 to $4 in the notes. That looks a bit different.
Yeah, the power law. Think of $23.44 as taking the whole block of $23 and multiplying it by itself 4 times.
So 23 times 23 times 23 times $23.
Right, and using the product law we just talked about, you'd add the exponents, 3 plus 3 plus 3 plus 3.
Which is just 3 times 4, 12.
Yeah.
So 212. So you multiply the exponents in this case.
Exactly. Raising a power to a power means multiplying the exponents. 2 after 12 times 4, 2004. It's like having groups of groups.
What's fascinating here are those special cases. Like anything to the power of 0 being 1. Why is that? $t equals $1. Seems weird.
It does feel a bit strange at first, but it actually makes the rules consistent. Think about our quotient law. $1.
Well, anything divided by itself is 1, assuming a isn't 0.
Right, but using the quotient law rule, that should be 1n, which is $a.
So for the rules to work seamlessly, $8 has to be 1.
Exactly. It keeps the system logical. And of course, $1 is just a itself, one factor.
Okay. And the source pointed out a really important detail about negative signs and parentheses, like $3 isn't the same as $3.
Crucial point. Order of operations matters. In $30, the 0 exponent applies only to the 3, so it's like $30.
Which is Micah 1. So Micah 1.
Correct. But with $3, the parentheses tell you the exponent applies to the entire base, including the negative sign. So $3 is 1.
And that applies to other powers too, right? Like $2 versus $4.
Absolutely. $4 means 2 C's times 2 times 2 times 2 power, which is negative 16. The power hits the 2 first.
But 2 to is $2 times doing 2 times negative $2. 4 negatives.
Yeah.
That comes out positive 16.
Exactly. The even exponent makes the result positive when the base itself is negative and inside parentheses.
So, okay, we've got these rules, these shorthands.
Yeah.
What's the big takeaway? Why are they so useful?
Well, fundamentally, they give us a way to handle and simplify calculations, especially with really big or really small numbers. Think science, engineering, even finance uses these ideas, like with compound interest.
Right, and they connect directly to roots, don't they? The flip side.
Exactly. Powers and roots are inverse operations. They undo each other.
We talk about squares like AGT2 and cubes, 3T rares. They're just specific powers, power of 2, power of 3. And the source mentioned squaring any number gives a positive. But cubing keeps the sign.
That's right. SAMP2 is 25s, but 5-3 is negative 125. And then you have square roots and cube roots.
The undoing part. The square root of 25 is 5.
Because 5 to 2 is 25 close. And the cube root of 125 is 5. Because 533 is 125 picks. The material also touches on how prime factorization can actually help you find these roots for larger numbers.
So why should you, our listener, really care about this beyond maybe a math test?
Well, the source had a neat practical example.
Yeah, they arranged anything. Like if you have, say, 64 students and you want them in a perfect square formation for a drill,
Yeah.
how many in each row?
You need the square root of 64.
Which is 8. So an 8 by 8 square. Same for planting trees or tiles in a square pattern.
It shows how these abstract math ideas connect directly to real-world problems involving area, space, even volume if you think about cubes. They describe relationships.
Okay, so we've taken a deep dive into exponents, their rules, product, quotient, power, and their inverses roots. We've seen they're not just theory, but tools for simplifying numbers and even figuring out practical layouts.
There really are fundamental building blocks for describing scale and how things relate mathematically.
It definitely makes you wonder.
Hmm.
We've seen this pattern here in operation, like powering and its inverse rooting. How else might this fundamental relationship between an action and its undoing show up? Maybe in other areas of math or science or even, I don't know, system design.
That's a great question. Where else do these core ideas of operations and their inverses appear? Something interesting for you to think about.